Welcome, ladies and gentlemen, to Integrated Math 2. In today's episode, we will be discussing Chapter 9.3.1, which is Average Rate of Change. At this level, the average rate of change is actually something you are all very much familiar with. You actually haven't seen it in this context before, but I think once we put it in the right frame, you will recognize the formula pretty quickly. So I'm going to begin with a formula you guys have learned from Integrated 1, which is distance equals rate times time. So again, let's just label these pieces here. This is the distance, and we know that r is the rate, and t is the time. Now, for purposes of this, I'm going to go ahead and solve for r, and the reason why I'm going to do that is because the title of the chapter is Average Rate of Change. So I'm going to want to get the rate portion by itself. So what I'm going to do on either side is I'm going to go and divide. Sorry, I got a little ahead of myself. Divide both sides by t right there. So r is equal to d over t. In other words, the rate is equal to distance over time. And there goes my rate right there. So as long as I can keep that in mind, that rate is equal to distance over time, then this lesson should hopefully make a certain degree of sense. We use average rate of change at this level so that we can understand something known as projectile motion. And so I'm going to start off with an example. And I'm going to start off with this parabola here, a graph, where instead of the traditional x-y axis, I'm going to call this the t-axis, and I'm going to go and call this the d-axis. D for distance, again, t for time, exactly like we have in this formula. And I'm going to go ahead and just draw a parabola that goes up and then down. Now, usually this is going to be used to model some type of thing, like if you throw a balloon in the air, or like a water balloon in the air, or you throw a ball in the air, they'll shoot a cannon up in the air and it's going to fall down. What you need to understand from this is, as time progresses, as time moves forward, the ball is going up and then down. So I don't want you guys to think that this is some kind of like distance horizontal versus distance vertical. It's not like there's a person here and there's another person here and person A is throwing the ball to person B. That is not what's happening. As time progresses, the ball really is just moving up and then moving down. So I'm hoping that makes sense. And what I'm going to do is I'm going to go and pick 2 points. I'm going to go and pick 2 points on this graph that represent the ball's position. Hopefully this makes sense. When the ball is right here at this coordinate, it's on the floor, so its y position is 0, but I'm not going to call it that. I'm actually going to call him, he's some value x and some value y. And again, he's on the x-axis right now, or the t-axis, so I know he's 0, but for purposes of this, I'm not going to call him that because we want to be able to find the rate, the average rate over, at any point on this curve, not just from the ground. Because this is going to be the first x and the first y that I generally label, I will call this thing x1 and y1. And then I'm going to go and pick a point on the parabola somewhere, like I don't know, like right here. And if this set of coordinates here is x1, y1, that means that this is naturally going to be x2, y2. So remember, going back to our original equation here, rate is equal to distance divided by time. So remember, that means that I'm going to take my vertical motion and I'm going to divide it by my horizontal motion, okay, or my vertical change divided by my horizontal change. So what is my vertical change here? In other words, how do I find the horizontal change from y2 all the way down to that line right there, to the same elevation as this? Well, that's easy. It's y2 minus y1. y2 minus y1. And then how do I find my horizontal change? I find my horizontal change by taking my x position from the second and subtract the x position from the first. And as we saw, rate is equal to distance over time. Well, it just so happens that the rate is equal to this. And we've seen this equation before. We have seen this before in the context of this being slope. And as you guys know, slope is a rate of change. So the connection that I want you guys to be able to make is that the average rate of change is the slope of that function on a given amount of time. Now, if you guys notice, if I connect those points, I've created a right triangle, which we used earlier on in the year to determine slope. This is a slope triangle. So what I've done is I have found the average rate of change of this water balloon on the time interval x2 minus x1. So, as long as you can keep this thing in mind, then you will be all set for the next few examples. Let me go ahead and put down a concrete example where we will actually apply this, and then you'll be done. And here we are. We are back with this concrete example here. I have an upside down parabola. Here's my d-axis, and here's my t-axis. And so I have a bunch of coordinates on here. If you want to, please hit the pause button and copy this parabola down with all the coordinates. And so what I'm going to do is I'm going to find the average rate of change. So we're going to find, let me type this out here, find the average rate of change on the given time interval. All right, so from here, let's go and give ourselves the time interval from, let's give ourselves the time interval from 0.25 to 1.9. So how does this work? Well, what I'm going to do is I'm going to say, okay, well, 0.25, that gives me a coordinate of 10. And then 1.9 gives me a coordinate of 82. This is going to require a little bit of a calculator because we've got some decimals going on here. But what I'm going to do is I'm going to go ahead and use my slope formula. So 82 minus 10 over 1.9 minus 0.25. So that's going to get me 72 over 1.65. And if I divide that by 72, I will get 43.636. So what that's saying is that that's the average rate of change on the interval from this coordinate here to this coordinate here. Your average rate of change, your slope, is 43.636. Okay, let's do another one. Let's do the time interval from 2.4 to 4.5. So again, what does that tell me? Well, at 2.4 comma 96, 4.5 comma 30. So into the slope formula we go. So 96 minus 30 over 2.4 minus 4.5. 66 over negative 2.1. So 66 divided by that will get me negative 31.428. Now, why is this rate of change negative? Well, that should make sense because from the 2.4 down to the 4.5, your slope is negative. And any change in position, and you'll learn this in physics or in calculus, a change in position is known as velocity, and velocity can be a negative vector or a positive vector. So there's some confusing terminology for you. Now, sometimes what they'll do is they'll say, okay, we want you now to find the rate of change at exactly t equals 4 seconds. Now, here's the problem, is that we don't have the tools to do that. That is calculus right there. To find the instant rate of change at t equals 4, we can't do that. But what we can do is we can squeeze this time between two times that we know, and we want to use the two closest times to get the most accurate time possible. So I will squeeze him in between 3.5 and 4.5. and then I will do the exact same thing as I always have. So this is 3.5 comma 78 and 4.5 comma 30. So I will get 78 minus 30 over 3.5 minus 4.5, which is going to be negative 1, and this is going to be 48. So negative 48. And there you have it. That is average rate of change. So in this lesson, we covered how to find average rate of change and how to use average rate of change to best approximate an instant rate of change. But as you guys move forward into your next levels of math, you will learn a formula that will allow you to find instant rate of change at any point on any function. And that will be in a pretty exciting time. So as always, please leave comments or questions in the questions area, and we will see you in the next episode.